I'll be talking about the modern CPUs, and by modern I mean the last 10 years and closer to the trailing end, to our end of the last 10 years. The subtitle is Optimization Techniques. I will show very few actual specific optimization techniques. So most of it will be about techniques you already know, but I'll talk about which techniques, which optimizations you should be paying more attention to. And there will be a few optimization techniques that I will actually show because they're less common, but for the most part, I'll be showing you things you already know, but you may not know which of them are becoming more important. Okay, so I'll begin by showing the picture view of the 10 years of evolution of the processors. Okay, those of you who have been to my previous talks of performance, about performance, know that I like this graph where I show the evolution of frequency scaling and transistor count over the last about 40 years. This graph is my favorite graph. It won't be here. I'm finally done with that part. I'll be only talking about the last like 10 years or so. So on the left is the Haswell, and on the right is, I think, Sapphire Rapids. So 10 years old CPU on the left, about a year old on the right. If you need help reading this, reading this die, this is kind of explains it. So multi-core structure, shared L3 cache. So by the way, one thing is, all of the CPUs we'll be talking about when I talk about comparing new and old, they're all multi-core. So we're way past the shift from like multiple cores. The interesting thing about the one on the right is it doesn't actually say where the L3 cache is. And that's because it isn't here at all. It actually sits on top of the whole thing. There is yet another die which you don't see, which sits on top of the whole thing and has the L3 cache. EPIC 3 one of the second latest generation AMD CPU, kind of similar to Sapphire Rapids in style. And here is actually something else that will come up later in this talk. These aren't die photos, these are package photos. Sapphire Rapid on the left and EPIC 4 Genoa on the right. There's something interesting about this picture. It's kind of, it may be a little bit harder to see on the left picture. Anybody notices like what's unusual about it compared to all the previous CPUs?
Multiple die.
It's not one die. So as I said, it's a little harder to see on the Sapphire Rapid. So here is the actual picture of it's kind of the overlay that explains what's going on.
And it's all scuffed too.
Sorry?
It's all scuffed. Go back to the last one.
Well, that's basically whoever deleted it did this. But so multiple dies or tiles, as Intel calls them. Okay, who here is used to the number of cores on the chip being 2, 4, 8, 16? Each of these tiles has 15 cores. This is a 4-tile version, but there are single-tile versions out in the wild. 15 cores. There are programs based on like the CPU info that actually have a bug on this because they expect the number of cores to be a single bit somewhere. Okay, so the multi-die structure will actually come up. In terms of the numbers, so enough with the pictures, in terms of numbers, the die size of a single die hasn't changed too much, about 400 millimeter squared. I'm talking about CPU only. There are CPU-GPU combinations that are bigger than that. Now we have several dies in the package, but a single die is about that big. Much higher transistor count, again, for CPUs, about 40 billion, more than that in things like Grace Hopper, which have GPUs on board. Clock frequencies are in the same range. Significantly more cores that comes with significantly more transistors and much larger caches. So this is basically the changes that we have seen in in numbers in the CPUs over about 10 years of evolution. Now, with all these changes and much bigger complexity, there are actually several major pitfalls that I'll talk about that can lead you to using your CPU really badly. So first of all, it has a lot more compute power, and I'm not just talking about the number of cores, that's concurrency, but also within a single core, it has significantly more compute power, which is great unless you aren't using it. It has significantly larger caches, which seems like, you know, should be a very good thing. Well, one, it actually makes up for the fact that memory performance hasn't grown up. Yeah.
Yeah, just seems like the bigger the cache gets, the slower it has to get.
The caches operate, well, L1 cache operates at the clock. So the caches operate proportionally, like at fractions of a clock frequency. Depends on the architecture, maybe even at clock frequency. They are, yeah.
So related to that, on the previous slide, you have 3 megabytes for L1 cache. That seems.
That's an Epic 4. Yeah, that's
L1.
Yep, that's Genoa.
Wow.
Yeah, these are the numbers for the latest Genoa.
Okay.
Public numbers. I just pulled them from their website, so I'm not disclosing any secrets here. Yeah.
For each core, I mean.
Mm-hmm.
You're saying it's still 3, even with a 3 megabyte cache, L1 cache, it's still 3 cycles?
It's well, it's however many cycles. I mean, L1 caches are like, you know, 2-4 cycles. It varies depending on the CPU architecture, but that number is largely the same.
Okay.
Now, so that last line was like the largest cache I could find. So it's, but you know, a megabyte caches happen. Okay, so much larger caches are great, but they partially make up for the fact that while CPU compute power is getting larger, the memory speed is relatively the same. DDR5, 8 channels, a little bit faster, but not as much faster as the CPUs themselves. So caches kind of make up for slow memory, and they do that only if you don't basically do something to disable them. They also have a much more complex internal state, and we'll see how that comes up. Okay, so let's start. So this is basically the outline of the talk. There are 3 parts. The obvious, the less obvious, and the surprising. Well, let's start with the obvious. Okay, so all modern CPUs, well, like general purpose processors, have the capability to execute many operations at the same time. First of all, they have Superscalar architecture, meaning they can actually execute, even in their scalar unit, they can, like integers, floats, pointers, they can do just under 10 typically things at like 7, 8 things at the same time. And then there is the SIMD unit, there is a separate memory access unit, there are other special purpose instructions that have their own hardware. Okay, so I'm going to just talk about Superscalar part, for which I have specific numbers, but it applies to other special purpose instructions. So if you look at the code that looks something like this, where I do multiple operations on the same values. The same values is an important part because if you involve more data, you have to read more data from memory. So that's a different story. That's involves memory accesses. Now I'm only talking about I already have, for the very first line in the loop, I have these values in the register, and now I'm doing more stuff to them. If you start writing this, now it's rare for your actual practical program to be able to do so much stuff to it. But if you start writing a benchmark like this, you'll find out that you can do a lot of these things at the same time, meaning you can add, so for example, if you just leave the first line, A1 plus A2 versus all four, is it the same time or different? Well, on most modern CPUs, it's the same time, practically the same time. You can add actually more, and at some point you will see it slowing down. So this is basically how it looks like. You have some data in the registers. You can do multiple operations on these registers at the same time. You can produce multiple outputs. So the first question, do the modern CPUs do more operations like in that superscalar capability? Can they do more things at the same time? On the right is the Skylake 14 nanometer Intel chip. It's about six years old, I think mine was. On the left is the Ice Lake, not the most recent one, but it's a next process, the 10 nanometer process. So it's now it's like the one generation behind. I'm running so what I'm doing here, I'm running a mix of instructions, which is kind of just where the old CPUs start to lose significant speed compared to a single add. I'm comparing to one add. And so I'm saying, okay, in the time it takes one add, can you also do for free a multiplication, a shift, a plus equal, other stuff? Okay, division is extra. Division is slow. So no divisions. But okay, and I got it. I loaded it to the point where Skylake is starting to slow down. It's running about 60%. So I reached the point where Skylake can't do like all 8 at the same time. Ice Lake runs at like over 90% of the speed of add, so Ice Lake is handling it just fine. Which means if you have the work to load it, modern CPUs will do more operations at the same time. If you don't have the work, you're basically wasting its capabilities. Getting that much work to be available, and that depends on the availability of the data, is a non-trivial exercise and may require you to restructure your code quite significantly to concentrate all the computations you do on a smaller amount of data. By the way, is that limited only to x86? No, not really. I don't have that much history on ARM as I do on x86, but these are 2 subsequent generations of ARM. On the right is the older Neoverse N1. On the left is the Graviton 3, which is based on a Neoverse V1. Same test for the same exact mix of instructions, except, I'm sorry, it's incorrect. Performance versus multiply. On ARM, add and multiply take significantly different time, and multiply is in the mix. So it should, I apologize, it should say performance versus multiply. Multiply on ARM is slower. And there are some multiplies in that mix. So these are also superscalar, and again, the later version can do more if you have more to do. So there is no specific optimization technique for it, although there are some optimization techniques that are based on this observation that I'll get to later. But there is no specific optimization technique, but there are basically they're usually program specific. You would want to restructure your code like maybe if you iterated multiple times over some array and did a little bit of computation and moved on, maybe now you want to coalesce it all in one place. So in practice, the superscalar architecture is primarily limited by data dependencies and memory accesses. So if you're memory bound, you're basically not getting a lot, at least from that part of the CPU enhancements. So one of the things you can do to help yourself to get more data if you're memory bound is it is more efficient to access memory in large words and using the vector instructions for that. Now, if you're not doing vector operations, vector reads doesn't get the data to where you want it to go. Well, there are instructions that will move like individual doubles or individual ints between vector registers and general purpose registers. And memory is slow, registers are fast. So reading in a big word and scattering it in registers usually pays off. Okay, the other part that actually helps you to still take advantage of the superscalar architecture is larger caches. And that's to hide the slow memory, and the pipelining, and that's to hide the data dependency. So modern CPUs rely on both caches and pipelining in general to a much greater degree than the older CPUs. Part of that is their compute power coming from their ability to do a lot of things at the same time, which depends on basically data being available, which requires pipelining and fast memory accesses. But you can also, unfortunately, disrupt both caches and pipelines. And if you do that, you'll pay much higher penalty now than you used to 10 years ago. So let's see how that works. Okay, step number one, we're going to completely destroy the prefetch. Well, that part is easy. So to understand what the prefetch does, okay, do I need to, who here doesn't know what the prefetch does? Okay, there are a few people, all right. Memory has two performance characteristics, bandwidth and latency. Bandwidth is how fast you can stream data continuously. Latency is how quickly, after you issue a request for a particular address, how fast is the response coming. On all modern memories, bandwidth limitation is much higher than latency in the sense that if you take a latency for every address and you assume that accessing the next address will take again that long and the next address that long and you convert it into imaginary bandwidths, you get a number that is much lower than the real bandwidths. So their memories are optimized for basically paying the latency once when you hit a range of addresses, and then it starts streaming at full bandwidth access. It's a slight oversimplification, but good enough for now. And prefetch is part of that. Prefetch is part of that mechanism that begins streaming data from memory in advance of when it thinks you will get to that address. So you hit the first address, by the time you get the second address in an array, for example, the data is already in cache, which only does you good if you're reading sequentially. If you're reading fully randomly, the prefetch can't predict where you're going to jump, so every hit in memory will incur latency. Bandwidth basically is out of the picture. So here is our very simple test for effect of random access. We have a container of data and we've populated it with some data, and we're just going to go and access every element in the container. That's all. And we'll compare two containers. One is sequential access vector, and the other one is a list. To kind of get us a prediction for what it's going to look like, we can get measurements from just run benchmarks on the memory and measure the throughput. When I say throughput, it's a combination of bandwidth and latency, whatever matters to you for this particular test. So throughput of sequential accesses versus random accesses, we're going to read, so this, and Now, the throughput depends on how big your memory range is. If it fits into cache, you get into L1 cache, everything is very fast. L1 cache is a random indexed array, basically. If you are in main memory somewhere here, well, so this is in nanoseconds per read. So multiple nanoseconds to get it from here. Now, if I have 1 million numbers, and numbers are 8 bytes, if I put them in a vector, I have 8 megabytes of data, and I'm accessing sequentially, so I'm here. If I put the same data in the list, first of all, it's 3 times more data because the list has pointers, and I'm accessing them randomly, so I'm over here. This is what we're going to expect. Let's see the actual numbers. So this shows the slowdown of vector versus list. So on the Skylake, list iteration is 38 times slower than a vector iteration. Now, by the way, when for list, you can't just say how vector is pretty stable. Basically, any vector of that size, of a certain size, will be that long. List depends on its history. The more you reshuffle the list, the more you allocate elements randomly, the worse it gets. So this list has been strongly reshuffled. So if there was some tricks the list constructor might have played for allocating all n elements at once, that's long gone. I erased one element, I inserted an element, and I did it many times. So it's now basically fully at the mercy of malloc. Same exact list versus vector, almost 100 times slower on EPIC 704 series. So no, sorry, 703, third generation EPIC. By the way, I'm showing kind of different representations of the CPUs. These trends are valid for all CPUs, but to a very different degree. So for a particular benchmark on some of the modern CPUs, you may find that for that benchmark, they aren't significantly worse than their 10-year-old cousin. They may be 15% worse. So yeah, I'm picking the most extreme examples, but I'm picking kind of from the same pool of CPUs, and I am definitely trying to impress the message on you that it's bad and it's getting worse. Random access is expensive. Next thing I'm going to do is I'm going to disable the cache. Anybody sees the difference? Okay. Everybody knows why this disables L1 cache. Okay, just a few people. Okay, is it okay if I leave this for the end, like as the first question, where we walk through the cache architecture and I explain why this little trick completely disables L1 cache? Okay? All right. So for now, take my word for it. I'll explain at the end. But this almost entirely disables L1 cache. Okay, so column major versus row major, or with cache or without. To be precise, with 1/64 of your cache on this machine. On Skylake, it's about 6 times slower to do row major access. On this EPIC, it's 22 times slower to do row major access. So that's how caches are important. They are much more important now than they were 10 years ago. ARMs, the same way. Not to that degree, but also remember, these are 2 subsequent versions of ARM. I don't have a 10-year span on server class ARM chips. So 2.5 times slower on Graviton 2, 4 times slower for row major on Graviton 3. Okay, so this is caches. The second trick the CPUs have that saves basically your ability to apply its compute power to the data that isn't that readily available is the pipelining. What the pipelining does is it breaks the data dependency. Here is the data dependency. We have 3 operations on this line, but 2, one of them has to wait for the result of the previous 2. So at most you can do 2 operations at a time. Well, that's not what modern CPUs do, and actually have been doing for quite a while. What they do is this. Yes, for any particular I, you can do 2 operations per cycle, or well, let's say for simplicity per cycle. It can do multiple adds per cycle, but let's say for simplicity per cycle, and on the next cycle you will do the multiply. But you can also do the next I at the same time as you're doing the multiply. So that's the pipelining. It pipelines multiple iterations of this loop, interleaving the iterations. Well, this only works as long as the processor knows what it's going to do next, because, for example, at some point, so this, as you presumably, is inside the loop, we're iterating over I. At some point, you'll hit the end of like the array, the vector, whatever, at which point you can't go to I+1. And that disrupts the pipeline. So any conditional disrupts the pipeline. So here is a conditional. We do some comparison, and then depending on the result of the comparison, we do different operations. That's the key. If you simply have something like return x greater than 0 question x colon 0, that still has the same may have the same. Some CPUs have instruction support for it, may have the same instructions. This has different instructions depending on the condition, which means you cannot prefetch instructions into the execution queue. Like execution pipeline is long and complex. I'm not going to go into that, but you read the instructions from memory, and then it takes quite a while before they're actually executed. So you don't know what to read until the very previous instruction is done executing, which means all that time that takes between reading the instruction and executing the instruction, you can't do anything, because you don't know which one to read. Well, that wouldn't do. So to restore their ability to pipeline, the processors now have, and had for a while, what's called speculative execution. Speculative execution converts your conditional code into non-conditional code. And it does it by means of branch prediction. At the point where the condition must be taken, the processor will predict, using some heuristics, which outcome is likely to be true. And it will go and start fetching those instructions, decoding them, scheduling them for execution, and maybe even executing them, if it takes long enough to figure out what the condition was. This converts your non-linear branched code into a perfectly linear sequence of instructions, so we're now back to pipelining. And life is great because we're now back to the problem that we know how to solve. Instructions are read, decoded, executed, and so on. Eventually, predictions will get confirmed long after the conditional instruction will execute it, and our pipelining is basically perfect until it's not. What happens if predictions is not confirmed? Well, first of all, obviously, everything you've done between the prediction and the non-confirmation has to be discarded. Everything in the pipeline is wrong. Everything that's currently executed is wrong. Everything that you load into memory is unneeded. So you have to basically discard all your current work. Okay, that slows the CPU down a lot, makes you work a lot harder. Believe me, that's not the worst. This is the worst. The worst is that in the process of doing the speculative execution, you might have done things that are basically impossible to do, or once done, impossible to undo. How do you undo an out-of-bound memory read, especially if you didn't have permission to read that memory in the first place? What about memory writes? Simple memory writes, which are legal, but the memory isn't versioned. Once you write, the old value is gone. Okay, what about writing into memory that you can't write into? Can you encounter undefined behavior while in the speculative execution stage? Yes, you can, like that. If the pointer is predicted to be not null, because it's almost never null, you will dereference a null pointer, so what's it gonna do? Well, okay, the answer is it basically, in the speculative execution phase, it can't act on any of this. So if it's kind of supposed to dereference a null pointer, it has to wait for confirmation that because it would be really bad if your program crashed and then they said, oh, sorry, we shouldn't have done that. Okay, so with all that machinery going on, how expensive is a branch misprediction? Depends on the length of the pipelines. It's always expensive. It has been expensive basically since branch predictors came online, and it's getting significantly more expensive. Longer pipelines hold longer delay between decoding a reading instruction from memory and actually retiring it. That's when the result becomes known. Means more stuff to undo, and in general, more complex internal state of the processor that has to be discarded and rebuilt. So conditional code, which was poorly predicted branches, more expensive. Again, true for both x86 and ARM. Oops, sorry about that.
Sorry, what was the cost on the left-hand side? Was it
times? How many more? So a mispredicted branch costs you 5 times more than a predicted branch. Well, in this case, 4 or 7. Okay. Now, there are. So, what's the message from this? Well, the message is obvious: make your branches predictable. Okay, there are algorithms where it's basically it's just the nature of the algorithm that you don't know which path it's going to take, and there is nothing you can do about it. So here is a simple one: binary power, modular exponent. Now, this particular algorithm is for modular, which is power of 2, which means instead of the modular operation, I'm using the bitwise operation here. But this is the classic algorithm for the binary power. This is like straight up from Wikipedia. As you can see, it basically looks at the bits, individual bits of this number and shifts. So it just keeps taking off the last bit and does something depending on whether it's 1 or 0. For general inputs, there is no way to predict what this is going to do. This is, basically 50-50 and random. Well, okay, if you can't make the branch predictable, what can you do? You can actually get rid of the branch completely. This is called a branchless transformation. And there on the right is that code. What it does is it always computes both alternatives. And then it selects the one it takes using the index. It uses the bit value as the index into that array. Remember, big difference between conditional data and conditional instructions. We're trying to avoid conditional instructions. Conditional data is fine. Conditional data basically just means there is an instruction on the CPU that will pick this register or that register. That's part of its execution. As it executes, it will take from this register or from that register and send it to the third. Yeah.
Is this going to do a round trip through cache on the right? Or do processors actually recognize that and do it in registers?
Oh, you mean will it have? It depends on the compiler. It's not a processor thing. It's a compiler thing. Now, okay, one of my pet peeves about the standard, they retired the keyword register. The keyword register was always optional, and the point of retiring it was that the compilers know better how to do register optimizations, which is absolutely true. But there was another point to it. You couldn't take an address of a register variable. And you just couldn't, it wouldn't compile. And knowing that you never take address of a register variable, compiler could do certain optimizations. Now, compiler could look at your code and figure out that you're not taking the address of this thing. But their ability to look at your code is limited by practical considerations, runtime size. So there was some value in basically asserting that you can't take an address of that thing. So today this depends on the compiler. Some compilers will notice that you never take an address of it, and therefore it does not need a memory allocation. Yeah.
Could it be that in the second case, so the CPU it has the res, and then it has to calculate the product and the end of modules, and then could it speculatively start this next line and see when the exponent is even, so it doesn't need to finish the...
Doesn't need to. See, doesn't need to. Yeah. Doesn't need to, because conditional instructions are your problem. It doesn't know what to fetch. The code on the right is just being pipelined. Just the width of the pipeline handles it. It interleaves multiple operations, multiple calls to this thing. Conditional data is a lot easier.
My point is, it can even...
Can the processor do reordering on data dependencies? Not, as far as I know, not any of the processors today can do it. The last one I knew that could do what you're saying is DEC Alpha. Now, there may be some trade secret optimizations that they added that there definitely are trade secret optimizations that I don't know about. One of them may be that. In that case, I don't know. But the last one I knew that could do what you just described is DEC Alpha.
So when I was asking about a round trip through cache, I mean, it looks to me like because it's an array, it's not going to try to keep X in a pair of registers.
The compiler would figure that. The compiler typically figures that out and converts it into basically, essentially question colon operator that gets converted into something like cmove. Okay. You would have to look at the assembly, but at least on x86, where cmove is readily available, most compilers, if they don't vectorize this, they'll do something like that. Vectorizing compiler, if this is in a loop and can be vectorized, will do something much better. AVX2 and in particular AVX512, if you have recent enough hardware, have what's called masked vector operations, where what they'll do is they'll convert that thing in the square brackets into a bit mask and hit the entire 8-element or 16-element array of these numbers with that bit mask and do 8 fetches in parallel.
Wow, all right.
And Clang is actually pretty good at that.
Fedor,
yeah.
Is there any value in removing the declaration above for res and just keep it as the 0th element of the array? Or is
typically we can try and see what the assembly looks like. Typically the compilers remove temporary elements, temporary variables as they see fit. So probably not, but we can look at the assembler. Okay. Now notice that this transformation is not free. There is a reason we do branches. Well, one of them is it may be impossible to do the if clause if the else condition is true. But the other one is it's definitely not necessary to do the if clause if the else condition is true. The branchless version always calculates both alternatives. The branched version takes the multiplication and the ampersand only if it's needed. So we're trading work for branch misprediction. Now, remember what I told you about the superscalar architecture. It has the ability to do a lot of work on a single cycle, probably more than you can ever send it to. And that observation is actually underpins all of this type of optimization. It can probably absorb the hit. Depends on the hit. If it wasn't a power of 2 and you stuck an extra % there, that's an expensive operation that overwhelms everything else. So there is a reason why I'm showing you, binary power of 2. The one with if modulus is not a power of 2, this is %, not ampersand. Yeah.
I mean, so if there are concerns like this, wouldn't it be better if the compiler just did this for them?
Compilers do some of them. They're getting better at basically recognizing patterns and doing it. This particular one they do not do. I haven't found a single compiler, and well, you will see this. I tried this on several compilers. Result looks exactly like that. So I haven't found a single compiler that knows how to do this. Now, on the other end of the spectrum, if I greater than 0, so return x sub I, otherwise return y sub I. Never mess with that. You can put x and y sub I in an array and return array sub I equals 0. Don't do it. All compilers that I know replace that by branchless. So it depends. The compilers are probably getting better at it, and the optimization can be expensive. So this is one of those optimizations that you never do prematurely. You profile it. So the cache optimizations, the branch predictor optimizations, meaning like making your code more predictable, trying to put more stuff into branches, like lifting branches out of the loops, all of these optimizations are just kind of fall into the category of not pessimizing your code. This is definitely a kind of on-demand optimization. As branch predictors are getting more, branch misses are getting more expensive, and on the other hand, the superscalar power is getting bigger, both trade-offs in this case point to one outcome. So this is on the Skylake, branched and branchless run at pretty much exactly the same speed, like 96%. On the Ice Lake, branchless runs 3.3 times faster.
You mentioned before the conditional move might be kind of a way to avoid doing
Not in the, well, the conditional move will probably happen here to implement the square brackets operator, but it won't, see, this actually avoids computations. The compiler would have to be damn sure that this is even possible before it does that transformation for you. Okay, these operations are, have universal domain, they're always possible. But in general, the compiler is really careful about, if there was a pointer dereference here, sticking it in here is something you might do if you know that it's never null. But the compiler would never be able to do that. So the compiler is pretty careful about doing this. Loading one of two values is a safe thing.
Can the processor speculatively execute the conditional move?
No, conditional move is a single instruction. It always executes in one cycle, and the result is one of the two registers and moved into the output register.
If you're pipelined and you don't know the thing that the conditional move is predicated on.
At the point where you execute, you do, because they're decoded way early. Yeah. They travel through the pipeline, and then it's executed. The one before it gets executed, and then this one gets executed. So they wouldn't be executed at the same time in the pipeline. They would be stacked, but they would be executed at subsequent cycles.
Okay, yeah.
One last thing here. Is there anything useful that you can say about dependency chains there?
I mean, pipeline is your answer to those. And again, if it's unconditional pipeline, just pipelines. And pipelines are generally wider. Like the more powerful the CPU, the wider are the pipelines. If they are conditional, so we have only one stage dependency, but you can have multiple, in an expression. Doesn't really, fundamentally doesn't change anything. Speculative execution context can be nested. Okay, so this is the first part. The CPUs are, in general, more powerful if you can use that power. They can do a lot more operations per cycle if you have the operations to execute. They have much larger caches, and as a result, take much bigger hit if you cripple those caches. They have much longer pipelines, and as a result, take much bigger hit if you cripple those pipelines. Most of my results are on x86, and note on ARM is they are superscalar and in general similar to x86 in this regard. Their relative trade-offs are very different, and I haven't finished, I'm not including like full measurements because I haven't finished my analysis of what they can and cannot do. All right, let's go to the second part, which is kind of things that after I explain to you, they make sense. And we're going to talk about concurrency in that section. Now, I must clarify, concurrency means different things to different people. We're talking about multiple threads running on multi-processor, multi-core machine with a shared state, meaning we have data shared between threads, we have locking or lock-free synchronization, and we're targeting high CPU load. What we're specifically not talking about is essentially separate threads or processes which are often pinned to a specific core, may be limited by latency, but very rarely, if ever, talking to each other. If you have that application, you have your own problems in the latency space, but on the concurrency, I envy you, but that's not what I just don't know that domain.
Sorry, I didn't quite follow. Are you saying this is, we're not considering like embarrassingly parallel?
No, because pretty much not, nothing of what I'm going to tell you impacts embarrassingly parallel. Embarrassing parallel is basically you take your box, you slice it into individual blades, and there is some I/O stuff that may affect you, and I'll mention that, but very few things affect you from what I'll be talking about. Okay, so the key part that is relevant for the modern CPUs here is that they have what's called non-uniform memory access. So we used to the picture where like there is maybe multiple cores, the thing on the right, L1, L2 cache, shared L3 cache, and then the memory is accessed directly from here. Well, that's not how it is anymore. The memory is accessed directly from here, but only part of the memory. Memory is divided into the NUMA nodes, and each processor has access to its own memory. Between them, they have this interconnect, which is some kind of fast link, QPI or UPI for Intel. I forgot what's called for AMD. But basically, it's a very high bandwidth interconnect that is used both to communicate between the CPUs, but also to maintain the illusion of global shared memory. It has a global address space, but all addresses in the global. You have a question?
Is this cache memory or?
No, this is DRAM. Yeah, the memory is DRAM. The box called CPU is like this box called CPU is everything on the right fits in that box called CPU.
So, and a memory access on another CPU can break the cache on
we'll talk about that specifically, but for now I'll say that memory access on one CPU needs to be facilitated, on a different CPU needs to be facilitated by the CPU that owns that memory. I'll tell you in a few slides how exactly that is handled, because that's important. Now, the CPUs in the last few years actually got worse than that. This now isn't the motherboard assembly. This is one package. Remember I showed you those EPIC 4s and Sapphire Rapids with their tiles and dies? That's how the package now looks like. They have multiple CPU dies. Each of them has its own memory interface. They have the interconnect that goes within the package. And that entire thing is then plugged into a multi-socket motherboard, which has non-uniform memory on top of that. So there is like a two-tier non-uniform memory hierarchy on these systems. whatever organization is one die on a package or one CPU on a multi-socket board, this group of CPU in its local memory, and by CPU I mean all of its cores and all of its caches, is joined into what we call a NUMA node. So you run threads or processes on this machine. Each thread at any given time runs on a particular core, which means on a particular CPU, which means on a particular NUMA node. Over time, they can move if you didn't pin them. Memory is allocated from, well, wherever you can get it from. There may be some affinity that the thread prefers to allocate memory on its local NUMA node. There may be not, but even if there is, sometimes you may have to access memory that somebody else allocated, and they may have done it on a different NUMA node. So in general, you have to access memory that is local to you sometimes and remote to you sometimes. Accessing remote memory is different from accessing local memory. Specifically, the CPU that owns that memory that sits on that NUMA node must be somehow involved. Now, the involvement basically there is an interrupt that makes that CPU fetch the address that you requested and then send it across the interconnect to the CPU that's requesting it. The manifestation of that is, well, the most kind of observable one is the memory on the remote node is slower. It's slower in both bandwidths and latency. You can measure the peak bandwidth. Again, bandwidth applies to streaming memory accesses, sequential access large amounts of memory. It's a 50% plus minus 10 slower. That number is remarkably stable, and I don't have that for ARM, so I haven't finished those measurements. ARM has very different memory architecture, so I don't know what that's going to be. On x86, it's remarkably stable in the last 10 years, 50-ish per, you get half the bandwidth, more or less. For a single thread, it varies a lot more. Even for one thread, some systems show significant degradation when you go remote, and some surprisingly don't show much. Also, newer systems typically have higher overall bandwidths, but higher penalty for going remote in bandwidths. Another important observation is that caches are still, well, L1, L2 are per core, L3 is per NUMA node, per package. So cache bandwidth is not affected by any of this at all, which means cache locality becomes a lot more important than it was before. By the way, on the multi-die systems, L3 cache is basically partitioned. So if you have a CPU like Genoa Epic 4 that has multiple NUMA nodes in a single package, L3 cache is partitioned. It can do some weird stuff, like it can actually change its configuration into 4 NUMA nodes or 2 NUMA nodes. So it can do some dynamic partitioning, but the cache is partitioned. For multi-die processors, obviously, you have 3 levels of hierarchy. Okay. So here is that memory throughput. That's a Cascade Lake, fairly old CPU. Memory bandwidths as a function of memory size. So in caches, you're fine. And as you can see, while you sit in cache, there is no difference between in-node and cross-node access because it sits, yeah.
How is latency affected across?
We'll get to that. Latency is important and bad, but we'll get to that. Okay, as you can see, once we get out of the cache, the difference between cross-node memory access and in-node memory access starts to become very visible. This is random access, which means this doesn't actually measure bandwidths. Random access is primarily determined by latency. So now let's talk about latency. Latency is actually behaving worse than bandwidth, unfortunately. The modern CPUs, the most recent CPUs, traded their higher bandwidth interconnect for higher latencies. Latencies on the newer CPUs, remote access latencies, are larger both in relative numbers, relative to the local latencies, but also in absolute numbers, unfortunately. Also, cross-node accesses always involve a last-level cache miss, because you have to go out of the L3 cache and into the interconnect and back into L3 cache of the other node. I'll show you what that looks like. Fortunately, cached data accesses are completely unaffected by NUMA as long as there is no data sharing. So large caches help, again, as long as there is no data sharing. Okay, so this obviously affects memory bandwidth programs more than CPU-bound programs. Again, data sharing will come in a moment. But if you have memory-bound programs, yeah, you need to worry about cache locality a lot more. Now let's talk about data sharing. There are different kinds of data sharing. Now, if you are accessing truly the same location, you have to have some kind of exclusion mechanism. Locking, atomic, something like that. This is pretty slow even on one CPU between different cores. Accessing different addresses within the same cache line is just really bad. It gives you all the performance penalties of accessing the same address with no benefits because you are not actually exchanging any data between threads. So it's called false sharing, just don't do it. Accessing different cache lines usually as fast as any other unrelated memory accesses, unless you are on the NUMA system. Here is a NUMA system, and what I'm going to measure is interleaved memory accesses, and I'm going to make sure each thread owns the entire cache line. So thread 0 is going to read this entire or write this entire cache line, and then some other cache line, and thread 1 is going to write, let's say, the next cache line, and thread 3 is going to write the next cache line. So there is no any false sharing going on. But we are on a NUMA system. Okay, there is some interesting stuff going on with the caches, but let's focus on this part here. This is the memory bandwidth for independent reads on all the so 32 cores running 2 threads each, hyperthreading enabled. And these are interleaved accesses down here. So interleaved accesses are like 100 times slower than non-interleaved, like fully independent access. By independent, I mean very far apart in memory space, completely not interleaved. It gets worse. I'm going to now lock all of the threads to a single CPU, which means I have to a single NUMA node, sorry, to a single NUMA node. I have 2 NUMA nodes, which means I'm basically using half of the CPUs on this machine for the same number of threads as I was doing on the full box. And I'm doing the same test for the interleaved memory access. It's slower than the non-interleaved memory access, but it's faster than using all 64 CPUs on both NUMA nodes. So I'm actually better off giving up one of the sockets and all of the cores on it. My program will run faster if I completely disable one of the 2 sockets on this machine. Okay, so what's going on here? Everything you knew about accessing the same cache lines on NUMA systems applies to accessing the same much larger blocks of memory, usually pages. So what you knew about false sharing, like don't access the same cache line from multiple cores, no, you get no benefit of data sharing and you pay the full price. On a NUMA system, the same thing applies to accessing pages. If you access the same page from multiple NUMA nodes, the entire page gets transferred to that NUMA node, or at least its ownership does. The whole page may or may not be relocated in memory, but the ownership of that page gets fully transferred to that NUMA node. There is a little bit more going on, and we'll get to that in part 3, which is just plain weird stuff that blows your mind. Okay, so data sharing on NUMA systems. Okay, true data sharing, well, when it's needed, you have to do it. But avoid the new kind of false data sharing, which is accessing the same page from multiple NUMA nodes. Now, true data sharing is usually unavoidable. Yeah, there are embarrassingly parallel things, but usually you would have at least the thread scheduler, like a thread pool, and the thread pool or some other scheduler would have the task queue, and the task queue would have either a lock or an atomic, if it's a lock-free queue, that all the threads need to access to decide who gets the first task from the queue. There's obviously some data sharing going on here. You need to have an exclusion mechanism to ensure that only one thread gets the first task from the queue. Okay, and that's where we get to fully embrace latency and the pain. So here is your data sharing as you know and hate it. Here is one core, and you have some shared location in memory, and it's not really in memory if you've been hammering it a lot, like the head of your queue in a thread pool. It's on L3 cache by now. Now, the cores don't really access it from L3 cache. They have to access it from L1 and L2 cache. So L1 cache is per core. So yeah, if you need if two cores bounce that shared value between them, it gets transferred through the caches of one of the cores to the L3 cache, from where it travels back up to the other core. Obviously, L1 cache is faster than L3 cache, so it's not good. But if you think that it's bad, wait until the next slide. Remember what the NUMA systems look like. These are your cores with L1, L2 cache and stuff. This is your L3 cache. This is your memory controller and the local memory. And this is your interconnect that goes to the other CPU. And this is your other CPU. So now it looks like this, which means if you're sharing data between two cores on one package, it looks exactly as it did before. If you're sharing data between two cores on different packages, your round trip now takes you out of L3 cache. It will register as an LLC miss. That's actually the thing I needed to get the Intel help on, because the profiler that reads the hardware performance counts, if this happens to you, it's just weird. VTune reports this as front-end stall, instruction decoding stall. Not, it reports the interconnect traffic, but it basically, huge interconnect traffic, completely unrelated to anything else. There's nothing else going on back end. All your problems are on the front end, and that's the CPU basically fighting this and trying to compensate for it and creating problems elsewhere. But the root of the problem is you have to get out of the last level cache and basically into main memory or into this interconnect, which is the same speed. I mean, in fact, it's the same interconnect that goes to memory and to the other CPU. So your transfer now goes from here all the way here. Yeah?
So when it's making this cross NUMA request, did it basically just stall the pipeline so much that it couldn't even fetch more instructions?
Yeah, so there is an interrupt issued on this CPU, which forces it to so first of all, the cache line gets dirtied, obviously, which means every access to that cache line gets delayed until the cache coherency machinery kicks in, and now it kicks in across. Cache coherency still works, but it now has to work across the interconnect. So the dirty caches are still automatically updated and reconciled, and if you try to read from the dirty cache line, you will be locked and will be waiting until it becomes non-dirty. But the fetch of the correct value into L3 cache, previously L3 cache always had the reference value, the absolute truth. The fetch was going into L2. Now, L3 cache itself is dirty. The fetch is basically going from main memory, or the other CPU, same bandwidth, same latency.
So you mentioned there was an interrupt.
There is an interrupt that basically requests CPU to actually commit its data. One of these cores has the absolute truth, currently holds it on the register. So there is an interrupt that requests that core to commit its data to the L3 cache from where it's being picked up, transferred. The L3 cache line is immediately marked dirty as soon as that core, the one on the right, modifies the value, and then everybody is locked pending the update.
So does the OS get involved then with that interrupt?
Not yet, but it will in a moment. In this particular interrupt, no.
Okay.
That's still hardware.
Okay.
It's going to get even worse than that. Okay.
Perhaps a similar question, but am I correct to assume that if one core is only working with L1 cache, like everything's in that cache, if the other cores try to access its memory, they won't affect its throughput?
If it's the same address, you are no longer working with L1 cache
No,
because...
not the same address, but like imagine they're working independently. One is just strictly in
Oh,
L1 cache and then...
Yeah, so cache locality is your savior here. If you have absolutely independent addresses, as long as they're on different pages, because remember, transfer is at the page granularity for some definition of transfer. But transfer is at page granularity. So as long as you're on different pages, if your core, one core and the other core on different NUMA nodes work on different memory pages, they don't know anything about each other. They're perfectly happy, and if it fits into L1 cache or L2 cache, whatever, they are as fast as they have always been. It's when you have a true sharing, at that point, unlike on a single NUMA node, you only had to go to L3 cache, and you didn't take the L3. You take L2 miss, but not an L3 miss. Here you take an L3 miss every time.
What's the latency of the interconnect? How many nanoseconds?
160-ish,
160. Okay.
which is a lot.
Yeah, it's a lot.
Yeah.
Did I understand you to say that the unit size that transfers across is 4K? Or
Not exactly. The reservation is for 4K. The transfer is still cache lines. But you'll see you'll see a little bit later what happens at 4K exactly. There was another question? No? Okay. All right. So let's confirm this theory by direct measurement. We only need one shared variable to confirm this. So here is simplest thing: atomic increment. Memory is on node 0, all threads are on node 0, here it is, the squares. This is the how many million atomic increments per second I can do depending on number of threads. Yeah, one is up there. Cross node, meaning all threads are on one node, memory is on the other node. And it's pinned. They are pinned to their nodes. There is no migration. Man, not bad actually. There is basically there is some penalty for accessing the remote memory, but I'm not memory bound here. Both nodes, memory is somewhere. Both nodes are equally involved running the threads. And now the pain begins. So it's actually better to have all threads going through the interconnect. Because what they do is they immediately pull that value into the L3 cache and sit on it. Because there is no reason to ever send it back to the other NUMA node. The absolute truth is owned, which is the true value, is owned by somebody within that NUMA node. There is never any reason to evict it from L3 cache. The fact that the memory location is elsewhere doesn't really, they're right through caches, but that happens in the background. Multiple 2 NUMA nodes involved, now you get the bounce.
Sorry, can you go back? But it's saying cross node is just slightly better than.
No, cross node is the yellow here.
That's
Oh, you mean on the 2 threads?
The orange line.
Okay.
It says cross node.
Yeah, for 2 threads, I'm not sure. This might be within the noise. I need to. for two threads, they're actually kind of staggered opposites, so I'm not sure what's going on.
But much better is one thread.
Oh, one thread is always way better than you pay heavy penalty for contention. When that is not new, that has always been true. Okay, so particularly read, modify, write, or just write operations have significant penalties on NUMA systems when multiple nodes are sharing the same location. Atomic loads don't, they're read-only. Atomic writes may or may not, depends on the system strongly. Some systems do, some don't. So RCU algorithms may have some advantage here. Newer systems have higher latencies in absolute terms. So QPI is around 140 nanoseconds, UPI is 160. Some of the older Intel systems like Haswell, some of the Haswell systems I have don't show any slowdown at all, but all the recent systems show pretty significant slowdown. x86 systems haven't done their ARM study yet. Unfortunately, most concurrent data structures have some shared state in them. Logs also have some kind of atomic variable in them. So the bottom line is maintaining consistent global shared state across NUMA systems is really expensive. Okay, so now I'm actually going to show you an optimization technique that I use. Skip this. All right, so we already covered the memory bound separation, one page. Okay, so I'm actually showing you specific optimization technique. Up until now, I was just attracting your attention to optimization techniques you already know. This one is lesser known, so I'm going to talk about it in details. So I have some threads running on multiple nodes, and I need a global state. Let's say I just have a simple thread pool and I need to know when to stop. I submitted a certain number of tasks. I'm counting the tasks that I executed. I need to know when the count is 0. Threads are running on both NUMA nodes. I could basically split it into entirely 2 separate thread pools and just run them per node, but then I have load balancing problems. One of them will finish way before the other. So I need essentially a shared count. Well, normally you just have atomic, stud atomic of unsigned long, and that's your shared count. On a NUMA system, that's going to get really expensive, as we have seen before, so that shared count, which is the value you decrement when the tasks are executed, is going to become the bottleneck of the NUMA pool, and I'll prove it with measurements in a moment. So here is your shared count, NUMA-aware shared count. So first of all, I need so I need my task counts per NUMA node. Second, this actually isn't good. I actually need to align them on cache lines. So I need to add a line S to make sure they're aligned on separate cache lines, okay? I can even spread them across multiple pages. It would be even better, but at least cache lines. Now, the trick here is that I do atomic operations on the per node count, and then I collect the data. So basically, this is what it looks like. I effectively do kind of split the pools, but not entirely. From the main thread, I can still submit the tasks to all threads. Each pool has its own count, and the main thread is the only one that collects the counts from here, which also minimizes the contention, because these threads have a heavy contention for their local count. They're all of them, let's say I have 32 cores on the node. All 32 are decrementing these counts, but they're within one node. Only one thread, which main thread, let's say it runs on a different node, only one thread is periodically reaching out and checking that same count. Better than all 32 of the other ones.
So the main thread is combining all the different counters.
Yes, the main thread is the only one that can reach to both pools and combine the counters. And when it wants, so essentially so there, typically in the thread pool there is some kind of flag that tells them to stop or like go to sleep or whatever. So the main thread will reach out and set those in all NUMA nodes.
Question.
Yeah.
If it's less work to do a push than a pull.
No, it depends on not even on which architecture. Like I've seen the different systems. So no universal answer that applies to all to all architectures. Now on x86, typically like read modify writes are everything. They take a full barrier, so they're basically.
If it's possible, a push can require less interrupts.
I don't know.
So if the main thread does the pull, like read,
the main thread does the reads.
Interrupt, right? Can you avoid that interrupt? On the node 0.
No, that you cannot avoid. NEX, that you cannot avoid. To reach into another NUMA node's memory address, you have to take that interrupt.
So let's say if node 0, like thread 1, let's say, writes something to node 2. So the interrupt would be handled by node 2, right?
The interrupt is handled by whoever owns that memory address at the moment.
Yeah, so then you don't need to do that interrupt on node 0. So it saves work on node 0 and 1.
You always do interrupt only on the CPU on the CPU whose memory is local. So that on the node whose memory is local. That's always true. Push or pull. Yeah.
If I want to show progress to a user, let's say the nodes are working independently on different nodes, the CPUs are working independently on different nodes, but I want to show progress. This node has finished this much. Would reading the progress counter there itself impact that node?
A little bit. I mean, users are slow creatures compared to CPUs,
Yeah.
so in reality, not significantly. No? Okay. You can do one better, because remember I said main thread submits the tasks. Well, you can actually, submitting the task involves manipulating of a whole lot of shared state in the thread pools. Well, you can do one better, which is you take a big batch of tasks, you ship it to a submitter thread that is now local to that node, and have it deal with it within the node now. Parcel it out to all the threads. Batch submit. Okay, all of this put together, here is the end result. Thread pool, throughput, the task that I'm running on the thread pool is very simple, very small, so it's limited. You can think of it as basically empty task. It's doing an increment. You can think of it as an empty task, so it's basically the throughput of the pool itself, how many tasks it can run, millions of tasks per second. As a function of number of threads, 2 NUMA nodes, 32 cores per node. No NUMA looks like this, and then it starts to slow down. NUMA aware thread pool, that's with all the stops. I pulled all the stops. Batch submitter, shared count, everything. 42. If you 42 millions of tasks per second compared to about 2 millions of tasks per second at one thread per core. So these kind of optimization techniques with hierarchical data structures are very effective on NUMA systems for shared state. They're also invasive. It's significant redesign of your shared data structures or your schedulers. Okay, let me skip this. Okay, and in the remaining time, we'll do the mind-bending part. I'll show you 3 real-life cases. So for these, I don't have benchmarks. This happened on a real application. I mean, I have benchmarks, but they're part of the real application. So first case, we get new, faster hardware. Yeah, it's NUMA, everything. All big servers are NUMA now. We get newer, faster hardware. Our program runs slower. In absolute terms, not just it doesn't gain from the hardware, slower in absolute time. We detect that the slowdown is limited to certain places in the code, and where it hits, it's large. It's 10x, up to 10x. The code itself is not actually bandwidth limited, is not really memory limited at all, is not latency limited. There is one commonality between all these places. They quickly jump over significant ranges of memory. They don't read a lot of memory, but they think of like iterating over the list of large data structures. You touch the beginning of every one. You don't read a lot of memory. You don't read the whole data structure. You just get like, let's say, 4 bytes from every one. But you very quickly traverse the entire data structure, which means all the pointers in the list node and, let's say, the beginning of each data structure. That's the kind of thing they do. The slowdown is also OS dependent. Somebody asked a question about the OS. Now you get to enjoy the answer. Okay, debugging. Well, first modify the real program, because I couldn't reproduce it in the benchmark. I took the real program. I put the problem step in a loop. Now I actually have something to measure. All I measure is that it's mostly in system time. Install the kernel symbols, get the root access, profile the kernel. Doing 2 things. NUMA management, like memory migration and all the related stuff, NUMA load balancing, and TLB updates. Okay, so what the heck is TLB? Now we need to know how virtual memory is managed, and that's on the OS part. So you have, on one hand, you have your virtual addresses. And on the other hand, you have the physical memory. Both are divided into the pages, and let's say 4K for simplicity. Like on x86, typically it is 4K, though there are different sizes. And each of the pages in the virtual address space is mapped to some location in the physical space. Well, each of the pages you use, you can reserve virtual address space and not map it to physical memory. You just don't use that range of virtual addresses. So physical addresses themselves, you don't know what they are. And all the processes running on this machine share that physical memory. Virtual address range is yours for your process. How is this mapping done? Because this is obviously important. When the CPU, your program only knows logical addresses. When the CPU issues a request, okay, read me something from memory, this is the address it knows. But it has to read from here. The data is ultimately in DRAM. So mapping is obviously important. Well, gets more interesting if you have, let's say, two processes, so 2 processes just have their own virtual address space, and with the exception of shared memory, they just don't point to the same physical pages and everything is fine. Okay, so how is this done? Well, there is a hardware component, memory management unit, which assists which actually does it. Like this MMU actually does the mapping. It has 2 things that it needs to know where the mapping comes from. It has 2 things that help it. One is the kernel page table. Kernel has the full mapping of logical addresses to physical addresses for every process running on your system. This would be painfully slow to actually go and look into that table every time. So there is a hardware component, translation look-aside buffer, TLB. And that's basically a hardware accelerated version of this same map. Now the TLB has the kernel page. The kernel page table has basically an entry for all, for all logical addresses that you have if they're unmapped, there is no physical address, but it has at least as many entries as you have physical pages, and if you have overcommit, it could have more. TLB has a finite capacity. It's a cache of some kind, so an associative table. So the OS actually maintains the complete map of physical addresses to logical addresses, and the OS is the only one who can. There is not enough capacity in the hardware to do it. So the CPU has that hardware accelerator, the TLB, that basically accelerates lookups of recently used addresses. When the MMU does the lookup, if it's found in the TLB, you have a TLB hit, MMU uses the value that's stored in the TLB. If it's not found in the TLB, it's TLB miss, the kernel has to walk the page table to find the corresponding logical address. A page table is actually some kind of, it's a tree-like structure, so you can walk it faster.
It's the OS that is looking up on the page table.
The kernel is looking up, yeah.
And then it transfers to the
MMU. So yeah, MMU triggers the interrupt, the control is, that's why system time gets involved. MMU basically delegates, stops your program, delegates execution to the kernel starts running, gets the value, returns it to the MMU finally.
Is that right on an x86? I thought the MMU will walk the page table on x86.
Sorry?
MMU on x86, the MMU will walk the page table, right? I think some other.
I think there's a hardware component like a page table walker.
Yeah, no, the ultimate, the full page table walk is done only in software. There is acceleration, but it's smaller in size. Yeah.
Is it safe to assume there's no kind of like prediction, like the hardware is saying, hey, I think this TLB entry is going to be accessed, so kernel, go look it up?
I don't know. There have been a lot of papers on that subject. I don't know if any of them have been actually used by hardware designers or not.
I think that the kernel only walks the page table when it's unmapped, right?
Yeah.
Once it's mapped, then the MMU can walk that page table.
I mean, there are like software managed TLBs, right? Are you talking about those ones?
Well, no, I'm talking about, once you are in software, you're already like way slow. There is a hardware, basically a cache, where you get like a single, order one lookup. You look up the address, and if it's in the hardware cache, it returns immediately. And then there is the software walk, which, I mean, the page table is actually pretty complex. It's a tree-like structure, and it has like optimizations for unallocated memory ranges. But once you have to walk it, you're in software, and if you turn on the kernel profile, you will find out exactly the name of the kernel function that does that.
But the thing is, like, it can be in the page table, just not in the TLB. In that case,
Yes.
the hardware is going to walk the page table. The kernel is not involved. It's just going to populate.
Well, according to the profiler, kernel is very much involved because that function, page table walk or something like that, depends on which version of the kernel you're in, shows up as the major CPU user, like pretty much the only CPU user.
Could that be to do with the NUMA?
Yeah. So now we get into the NUMA part. Kernel page table is one and only. TLBs are per CPU per package, or per socket, or per NUMA node, basically. Unlike the caches, which have the whole hardware coherency machinery, there is nothing like that for TLBs. TLBs can get out of sync, and the hardware doesn't care and doesn't even know. If that happens, it's the kernel's job to put it back into place, because it would obviously be bad if two different NUMA nodes pointed you to two different physical pages on the same logical address. The mechanism by which the kernel does that is called TLB shutdown. Kernel detects that it might happen, stops everything, flushes TLBs, and rebuilds them. Okay, what can trigger TLB shutdown? Now, again, there is some work on hardware optimized TLB shutdowns. As far as I know, hasn't made it into actual production yet. What can trigger TLB shutdown? Some memory access, particular memory access kinds, nothing that is involved here. NUMA page migrations. if the kernel migrates the physical page from one NUMA node to the other, because the locality, like these threads are accessing it more often, and kernel in general does like to balance, like move memory closer to the threads, the thread that receives it, the NUMA node that receives it obviously has to map that physical page into its TLB. But the virtual logical addresses haven't changed, but the physical addresses have. The NUMA node that receives it would map it into its TLB. The NUMA node that lost it doesn't know what that is, has no way to access the other TLB. There is no hardware protocol for that. So the kernel basically has to update the TLB of the NUMA node that lost that page to match the NUMA node that received that page. And the TLB shutdown is actually mentioned in the name of one of the kernel functions that shows up in the profiler as handling this situation. Yeah?
What about allocating and deallocating memory? Like, would those count as explicit changes to the page table?
Sure.
So if another thread in your process is allocating and deallocating memory, that could cause your TLB to...
Well, see, TLBs do not get updated when you just allocate and deallocate.
It is large enough to allocate a whole page or something.
Well, the kernel would write into both if there is empty space. So, I mean, the kernel is the one who does the allocation.
Yeah.
So if there is empty space, and I don't know what the strategy is for handling empty spaces. Is it greedy or basically is it lazy or greedy? But assuming it's greedy, it will just write into both. So TLB shutdown is what basically takes 90%, and handling of this TLB shutdown and the functions related to the migration update is in the profiler, shows up as 90% of the runtime for that section of the code. 10% is for your program, 90% is for the kernel. There isn't a whole lot you can do about it except one thing. You can increase the page size. Bigger page size means fewer entries. In the page table means TLB with the same capacity can cache more entries. So yeah, huge page tables.
If you have huge
pages,
does that mean your NUMA granularity is?
Your NUMA granularity is larger. You have to pay attention to that. Because huge page tables transparently and kind of automatically break into small ones if you do things like migrate parts of them or advise parts of them.
Okay, it'll do that.
It will do that for you in a kind of transparently, automatically, and it won't put it back. Okay, so all right, so we talked about true sharing. We talked about like hardware-assisted profiling and how it's sometimes useful and sometimes misleading. Okay, let's go quickly through another real-life case. Again, the beginning of the story is the same. We get new hardware, the program runs faster. The slowdown this time is spread across the entire program. It's not affiliated with any particular code location, but it does show up as an overall low CPU utilization. CPU monitoring shows about 70% CPU load. And OS level measurements show significant idle time. So this is what it looks like. We have the monitoring. So the top line is the loading, the bottom line is the idle time. 256 cores are on this machine, so this running at like 150-ish cores isn't great. Okay, we do some tuning, some kernel of tuning. These are EPIC processors. We get a little better. So what's going on? The fundamental kernel tuning that we had to do has to do with this kernel migration cost. And that is basically how quickly a process can be migrated from one NUMA node to another. Lower values make for easier migration, so we had to lower the values. What's the problem with the migration? Well, in our case, See, we have a multi-threaded distributed application, which means all threads, in addition to doing their stuff, they also talk to the network. Now that actually doesn't happen often. In a normal situation, that does not happen often enough to be visible in the CPU load. We still run typically at 100%, so like 98% CPU load. But in this case, there is only one network card on the system, and it's physically attached to the NUMA node 0. It's sitting on its PCIe lines, which means every time a thread wants to talk to that card, the OS says, oh, you're talking to the NUMA node device. Let me move you to that NUMA node. Now that node is overcommitted until somebody else can be moved over there. And that default kernel configuration is pretty long on that. And when it stops talking to the network, and as I said, it doesn't talk to the network for very long because we do maintain very high CPU load on average, it's still sitting on that node. And it will sit on that node for a while because, again, OS has a high resistance to migration. So even though our network overhead is negligible, because of the asymmetry between the NICs and the NUMA nodes, there is an extra migration overhead, and that is very much non-negligible. So we effectively basically overload one node and idle the other node because the OS doesn't rebalance fast enough. Okay, so IO-bound programs in general need to worry about that. Okay, final real-life case. This one you need to know. Program, again, same story. Program runs slower on the newer hardware. We buy new hardware, very expensive. Program runs slower. The slowdown is not associated with anything specific code, but it does occur in the best scaling, most parallel sections of the code. The CPU utilization this time is 100%. Fortunately, we have excellent monitoring, and that's actually one lesson from this talk. Have good timers and monitors coverage as a part of your application, not just in the profiler, as a part of your application. Monitor everything. On the vertical axis is the clock frequency. That big arrow is the best scaling part of our program. The processor can go to boost to 4, but 3.3 gigahertz. And it drops to 2. The problem is, it's spec'd as 3.3, but it doesn't have enough power to run at 3.3 all the time on all the cores. It has a 240 watt power envelope, which for that hungry beast isn't enough. How do I prove that that's the case? Okay, here is a version of that, of a similar, same series, different model, 320 watt CPU. That one has enough power to run all of its cores at full. It also has slightly higher maximum clock frequency, 4 point something. Now everything is perfect, no slowdown. When you're buying those CPUs, read the fine print. Some of them are not able to deliver everything they promised to deliver. They are targeted for low latency applications where the burst speed is needed and the overall load isn't high. They say that that's the case. They're also cheaper, and by the show of hands, who has the bin counters who would read the fine print and know the difference between low latency and high throughput? Okay, so there are a few lucky people in the room. Or maybe they're the people who actually approve the purchases. We're sitting on this pile of stuff that, it gets worse. You optimize your code to make it more efficient. The processor fights back because it lowers the core speed, the core clock. Okay, so conclusion. Modern CPUs basically like things to be smooth and predictable. Memory access is predictable, branch is predictable, they have long pipelines, they have complex internal state, and they go to great length to try to maintain it all in the face of all the semi-random events that happen when your code runs. So basically to help them use fewer semi-random, try to trigger fewer semi-random events. They can do a lot of stuff at once, both on their superscalar units and on their other special operations like SIMD, which means you can trade compute costs, computations for predictability. These optimizations used to be rare. They're now becoming fairly common. Memory sharing is a whole lot more complex on all the modern systems because you have these NUMAs and hierarchical NUMAs between multiple dies and multiple sockets. Memory sharing isn't as simple as it used to be when you just have a cache and cache lines. Effects of NUMA systems, we probably don't even know them all. They involve a lot of weird things like OS and its data structures, and memory addressing, and I/O interactions, and some of them are disproportional, like in our case, I/O interactions, which is negligible in both time and volume, actually had a significant, about 30% penalty on the overall performance, not because of the traffic we were sending, but simply because of its interaction with the NUMA system. And selecting the right processor for the job isn't as simple as it was. Okay, so how do you deal with this? Profiling and monitoring, data collection is very important. Profiling helps you to find problems when you know you have a problem. Monitoring helps you to both discover that you have a problem and also collect the data that will guide you to the approximately the right place so you can begin profiling. I can't overstate this. Monitoring, so collect all sorts of extraneous things. CPU load, clock frequencies, network traffic if you have network. Yeah.
But do you do that using the OS tools, or you
do that using
instrument your code?
I instrument the code to call the OS specific functions. Now we typically have a monitor thread or a monitor process, so we don't do it on the main. On the main thread, we have like a monitor process that runs and collects. These are global OS specific stats. They're typically not per thread.
And do you do that unconditionally, or you have different?
I do it unconditionally. You can configure. I mean, there is a configuration variable, like in the config file, there is an option to stop it, but the default is to run it. You can configure the time interval, like how often it gets collected. But our default is to collect everything at some non-disruptive range of time, like 3 minutes. Also, it's helpful to know your hardware, and the way you know your hardware is to collect a library of benchmarks. You begin with a few known benchmarks, like what I've shown you, and as you encounter these problems, sometimes you can add a small benchmark. For example, if you run into a branch prediction problems, okay, I know now that I have to pay attention to branch prediction. When I get a new CPU, I need to quickly evaluate how expensive is a branch miss cost on that. Well, I have a small benchmark for that. That'll give me an estimate of whether I should worry about branchless optimizations on that processor. So collect that library of benchmarks. Yeah.
So let's say I'm developing a program or a library and I don't have all the CPUs. What is the cheapest way you would recommend for me to be able to simulate or test what the performance characteristics would be on different types?
I haven't worked with emulators. I don't know to what extent they can reproduce this. You can rent 2 generation back CPUs pretty cheaply. These days, for example, like something like DigitalOcean, which is pennies per hour, they have 2 generation back. So if you want Epic Force or Sapphire Rapids, I don't know where you can get them. We work with the manufacturers because they want our product to run on their CPUs, and I actually don't have our own Sapphire Rapids, and I have only a handful of Epic Force. And I had to rent Graviton series from Amazon because we don't have any either. So the availability of the latest hardware, well, you bug these guys. Send them your benchmarks and beg them to run them for you.
Well, our colleagues maybe.
But like 2 generations back, you can get a lot of stuff from like cheaper cloud providers. Yeah.
So I'm writing a program that has to crunch a lot of numbers, and I want to do it as quick as possible. How can I say that, oh, I want this to happen in a single NUMA node, or what do I put there on my C++ code?
What do you mean in a single moment?
In a single NUMA node.
Oh, in a single NUMA node.
So
Okay.
it doesn't
Okay.
go.
All right. So there is the whole. So this is OS specific.
Mm-hmm.
So I know how to do it on Linux. But there is a whole interface. It's called NUMA-CTL, and it has a bunch of functions which allow you to restrict the current thread to a subset of CPUs, and including the subset CPUs on a specific NUMA node or any other subset of CPUs, and restrict the memory that that thread can allocate to this, like the same node. Obviously wouldn't be a subset of CPUs, but to a same node or some other node. And if you want, force to migrate some other memory from another node that you want to access on this node, you can request a migration. So there is a whole lot of APIs that allows you to limit both execution and the memory. Now that requires coding. So before I do any of that stuff, typically what I do is there is also command line interface for it. On Linux, again, it's a program called NUMA-CTL. It has a bunch of options. It invokes other programs. So NUMA-CTL options, name of your program arguments. And what it does, it basically fools your program into thinking that other CPUs don't exist. Or so you can say, okay, the program that I'm about to launch is only allowed to run on NUMA node 0. And is only allowed to allocate memory from NUMA node 0. So that would quickly tell you if, like, you get some benefit. Basically, if you have a sensitivity, you may not be able to simulate exactly the conditions, because from inside your program, programmatically, you can do a lot more fine control. But you would at least be able to estimate sensitivity. So you can say, for example, lock all my threads to node 0, lock all my memory to node 0, now lock all my memory to node 1. Did that matter? Okay, if it mattered, like memory locality matters. If it didn't, memory locality itself doesn't matter. Memory sharing can still matter. Then you can say, okay, bind my threads, half of them to node 0, half of them to node 1, put memory on one node. Did that matter? If it mattered, bouncing memory between nodes mattered. So you can do, you have a pretty crude level control, but you can at least detect sensitivity of your program to this type of thing. And that will allow you to start putting more fine-grained controls in your code. Yes?
Do you know of, and if so, would you recommend any libraries that provide higher level abstractions for things that are, for data structures that are like NUMA oblivious, let's say?
I don't know. And so I don't. When I was writing this thread pool, I actually looked at ASIO, which I think was a candidate to adoption in the standard, maybe still is, I don't know. And on a NUMA system, my pool was like about 50x faster than theirs. And that's kind of one of the most common libraries. So at least, and that was about a year and a half ago. So that was when I wrote this NUMA pool. So at least that library clearly doesn't do anything particularly good for NUMA, maybe nothing at all. I don't know if there are specific NUMA aware these hierarchical data structures in a kind of open source library. Any other questions? Yeah.
Yeah, it was like a side note maybe. As far as I remember, with ASIO you can also put your own scheduler. So basically you could kind of, make it run on NUMA node.
Sure, if I write my own schedule, and the point was to see whether theirs is NUMA optimized. I mean, I already have my own scheduler. Okay, I'm out of time. I promised you an explanation about the caches, so if you want to stay after the talk, I'll show you how the column major order bypasses the cache completely.